I have been working on Lagrange points for a while. And this is really where I wanted to get to. There's some other stuff I wanted to do. And there's a whole playlist with all my Lagrange point calculations. Some of them aren't great. Some of them are. But I encourage you to check out the whole series. This is part of a series. So what I want to do is to look at the stability of the different Lagrange points. So what the heck is a Lagrange point? Okay, let's start from the beginning. So here I have a binary star system. I have mass M1 and M2, and they're different masses, but they orbit each other around the center of mass. So they have the same angular velocity, but they move in different directions with different radiuses about the center of mass. And so that's the first thing you got to set up. You got to do that. A Lagrange point is a place where you can put an object, a low mass object, so it doesn't influence the motions of these, but such that it will have the same angular velocity as these two. So that means that as these rotate around, this point down here, one of the Lagrange points, L4 or 5, I can't remember which one's which, it will move the same way. So if you were at this star, that would be in the same location relative to all the time, and the same for that one. So that's a Lagrange point. There's 5 points. L1 is right here, such that the net gravitational force between these two make this move with an angular velocity equal to those angular velocities, but it moves in a different radius circle. L2 is on this side, so that both the gravitational forces are pulling in the same direction. L3 is over here on the other side of this planet, so it's a lot like that one. And then 4 and 5 are in a path above and behind, in front of and behind, not necessarily in the same path as this planet or star. So the way that you calculate the location of point L4 is to make an equilateral triangle where the distance between the two objects is r, so it's not the center of mass, okay? And then make that equilateral triangle with those two at the points and L4 at the other point. And so there'd be another one up here, L5. And I don't remember which one's which, doesn't really matter. I was going to put it up here, but I ran out of room. If I do that, if I have these at equilateral triangles, I can show, and I did this in a previous video, that the net force vector due to the gravitational forces between these two points to the center of mass. And since everything needs to rotate around the center of mass, this makes this have a circular acceleration that makes it move in a circle around that center of mass. And you also want the angular velocity to be the same, and I do show that that does work out when I modeled it. But what I want to do now is to show that L4 is stable. And to be stable, that means that if I displace it a little bit, if I'm not right on the point, then it comes back to that point. L2 up here I showed is not stable. So what I did, and this is with a Monte Carlo calculation, which makes a bunch of random values. So I have generate some random points up here, and I'll let them, for each of these points, I calculate the two gravitational forces due to these masses, and then I just let it go. I give it an initial velocity such that it has the same angular velocity as these, and you can see that unless it's right there, right at L2, these other points, they either curl around here or they shoot off into space. They're not stable. What I want to show is doing the same thing for L4, and hopefully we can see that even if they're not quite at L4, they still stay near L4 or get pushed towards L4. I don't know if it's going to work, okay? But to do this, we need to make this binary star system, which I've made many times, and I'll try to include all the important links at the bottom of this video. I don't normally do that. I just make one video and put it in a playlist. But this one's my favorite, and I haven't even made it yet. And that I need to make a list of these points, calculate the gravitational force in each one, and then model it. So for each point in my list that I make, I'm going to first randomly create it around there. And then I need to, number one, calculate R1 and R2. These are vectors technically. So this is the vector from mass 1 to that point, and this is from mass 2 to that point. I need that because the next I need to calculate the gravitational force. It's going to be equal to negative g m1 m over r1 squared r1 hat. So I need that vector so I can calculate the vector force. And then I need to do that for both forces, F2. After that, I can use the momentum principle to update the momentum of an object right here in a short amount of time. So I'll skip the steps, but this says that the momentum after some short interval, which I'm calling P2, is momentum at the beginning of that interval plus the net force times delta t. So I need a time interval that makes sense, right? So and this is assuming that during my short time interval, this force is fairly constant. So for stars, that short time interval could be 500 seconds or something like that. After that, I can update the position of my mass here. I'll just say let's call it RA is the position of that. 2 is RA1 plus P2 over MA delta T. So this just comes from the definition of average velocity. Again, I'm assuming the momentum is constant during this time interval, which is not true. But for short time intervals, it works. And then just do that all again and again for every single mass. And so since I want to do it for every single mass, I'm going to have all these masses in a Python list. And then I can just pass through the list and to calculate. And I already did that for L2. I'd want to do it for L4 actually in the same program, just so it can look really cool. So let's jump over to Python and let's see if we can get this to work. And I haven't done this already, so it may be a complete and utter disaster. I'm willing to take that chance for you. Okay, so let's see. Here we go. I have here a couple programs already open. This one is I built a function that can calculate the location of L4. And that's what this is right here. I'm going to go ahead and copy that. And I'm just going to paste it into my other program. And then up here, I have a function that calculates L2. Okay. Now, there is a really big difference between L1, L2, and L4 in that in my L2 function, I'm assuming the planets start on the x-axis, so I'm just calculating that distance. But in this case, I need two things. I need the distance of the, actually, let's see if I can move my picture over here because I just realized you can't really see me. The distance from the center mass, but also where it is. So I need a vector value for that. In order to do that, I need vector values for the location of the two stars. So let's just run this as I have it now before I get started. So this is my L4 calculation. I'm sorry, this is L2. So there I have 50 points that start random places, and most of them, one got ejected just because of a calculation error. But let's change this to down here. So what I do is have balls. I'm gonna have to make a new name for my other list because I want to keep this in here. And let's make this a list of just 5 balls and run it again. Okay, so that's actually pretty cool. So you see that one little bitty one staying there in stable orbit. That's I put one at L2, and the others I just put around L2 using some random numbers. So every time you run this is going to be different. Okay, so now I want to do the same thing for L4. So that's the first thing, is to copy this function L4, go back over here and put it in. I've already renamed this, and yes, I will give you the code. Calculating L2 is actually not trivial because it's a very difficult equation to solve, but this one's not. This one I have to input mass 1, mass 2, and the vector locations of those. So let's just make a list with one object in there, and that one object is going to be right at L4, and then we can add things later. So I'm going to do it. So this is my loop where I calculate all the forces. So let's just do it right here. Let's say balls 4 for L4. It's going to be a list, an empty list. And the first thing I'm going to do is to calculate my temp vector. I can call it RT. I used RT up here. I can do it again. RT equals L4, M1, M2, and since it takes C's going back up here. L4. I need M1, M2. I need the vector R1 and the vector R2. So the vector R1 is going to be star 1.pos. The vector R2 is going to be star 2.pos. And that should give me the location of that object. And let's go ahead and put an object there, but not animate it. Just put it there. So I'm going to say balls 4 equals balls 4. Actually, I don't even, let's just do it this way. Let's just start it with a list, an item in there. So I'm going to say sphere. Oops. The position is going to be RT. The radius is going to be the, I'm going to make it a little bit bigger than the other one just for now. So R divided by 40. Make trail equals false, just like before. Let's make it, so I got yellow for 1 star, white, cyan. Let's try magenta. Color equals color dot magenta. Okay, let's just print, let's just run it. Let's see what happens. There it is. Okay, so it's not updating, it's not moving or anything like that, but it is there. It did make it in the correct location. I'm pretty happy. It seems to be the correct location. It's right on that path, but I think that's okay. So the next thing I need to do is to give it a mass. Actually, I'm going to put that in here. Let's give it a mass of 1,000. So I'm going to put in here a parameter m equals 1,000. It doesn't really matter what the mass is, but it needs to be mass. And same thing I did up here. And let's make it back to, let's make it 50, a little bit bigger. Okay, so now I'm going to do the same thing up here. I have n is the number of items, and then n is a counter. So in this case, let's say n4 equals 4, and then n4 equals 0. So n4 is my counter, and these are the number of things I'm going to add on top of what's already there. I'm going to do the same thing I have here. So I'm going to say while n4 is less than n4, and there's other ways to make lists, but it's important to make a list that makes sense to you. Okay. If you run code that you don't really fully understand, it's better to do it in a long, more complicated way that you understand than a way that's elegant that you don't understand. And I'm not a perfect computer programmer. I'm never going to say that. Okay, so let's make, just like up here, let's make a temporary. So I went through and made all those balls, so I can reuse this RT. So actually, let's just do this exact, I'm going to do the exact same thing. I'm going to spread them out over some distance. That code is identical to what it was before. All right, so I'm going to generate a random number, which random gives a value between 0 and 1. I think there's other random functions in this version of GlowScript Python, but let's just stick with this. So I multiply by 2, so now I have between 2 and 0, subtract 1, and that gives me a value between 1 and -1. So when I place these things in the x and the y axis, they could be between, you know, drt, which is my space size, to negative drt. So I'm adding it to that. But I need to add it to my, that's how much I'm adding to that little value. Then I can say, I'm just going to do the same thing. I don't need that print statement right there. So let's just copy this, because it's essentially the same. But I need to change, I made them 50. And I need to add a color in there, because the other one was just white, which is no color. Color equals color dot magenta, comma. Okay. Now I'm looking back up here. Now I need to add one. N4 equals N4 plus 1, and that finishes the loop. So if when I run this, I should get 5 masses at L4. Let's just run it and see if that does it. Yep, there they are. Okay. Now, and every time I run it, it should be, ooh, it gave me an error. Undefined object. Balls I. Oh, you know what? Balls 4 equals balls 4 plus position. And so what happened was I added to the list, and I think that's all I need to do. Let's see if that fixes it. Yeah, okay, that looks like it's working. Okay, so now I need to give those balls an initial momentum that gives them an angular velocity so they can go around. That's what I want to do next, which I did up here. So I can do the same thing up here. I'm going to copy this. That's for the previous balls. And then I'm going to say for length of balls 4, balls 4, balls 4. And what this does is it finds the momentum based on the angle. It's r cross p. So it uses the angular velocity omega, which I have calculated as a vector for my other objects. And so that's that. Now they have a momentum. So down here, I can do this. I'm going to do the exact same thing. I'm just going to copy this whole thing and do the exact same thing. Because now once they're in this situation, ooh, that's wrong. Okay, it's the same thing, right? I'll just have changes to balls 4. Balls 4, balls 4, balls 4, balls 4, balls 4. If you don't say it, it doesn't work. I think this is going to work. If it works, I'm going to give myself a double high five, but it may not work. Okay. See, it didn't work. Inconsistent indentation. Oh, yeah, that's off a little bit. Let's see, so let's just delete that, tab, and let's do this, fix this one, tab. Okay, that looks right now. That one's off by 1 space. If you don't like Python, it's because of the dependence on, ooh, it worked. But you'll notice that they're not quite stable. Let's see if maybe they're too far off. Let me start them off closer, a 1% difference. Okay, so it's not 100% stable, but you will notice that they're not far off. Let's change that color. I cannot see that magenta. So let's change that to yellow. Even though we have a yellow in the center, yellow shows up really well. Yellow. Yellow. And there you go. Okay, so now I want to make more masses. So that's just with 5. Let's make a whole bunch. They're not completely, ooh, look, they are coming back. They're not, it's not crazy bad. So let's go up here, and for the first case, let's do 10 at L2. And let's do, how many at L4? Let's do 30. I don't know, I just picked 30. Oh, I didn't like that. Undefined object. Well, I just changed N4 equals 30. I changed N10 equals to 10. I had that at 5. N4 equals 30. 4. Why is it not working? Huh. That's weird. Let's just put this N4 at 10. Okay, so I'm got a, oh, I think I have this, maybe this I is messed up here. Let's see. Let's just print here. Let's just see if it gets there. Here, okay, got there. This is a great try. You know, you might want to think, hey, maybe he's doing this on purpose. Oh, I know what it is. 4i in range len balls. For, I think maybe if these two aren't the same value, it's going to cause a problem. So let's say print here, which is dumb to do in a loop, but it did not get there. Okay, so if I put it up here, oh, it did get there. It didn't get down here, though. See, it did not get there. Okay, so let's do this. Let's change this to J. 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 Oh, that's where it is. Look at that. That's where it is. I didn't even need to change it to J. But I need to change these now. What's a program if you don't make a mistake? It's no fun then, right? Okay, let's run it. Oh, crud. Undefined object. J number. Oh, I think I just... J.M. Balls for J.M. Balls for J.POS. Oh, here. I missed those. It's weird. Okay, we're getting closer. I missed another J. 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 Let's put my little print statement in there. Okay, so it got there. Oh. No. Balls type number. This code does not really help me. Balls.length plus. So it's getting there. Wait. Balls. Balls for. Aha! It's just dumb stuff. You just make dumb mistakes. It's fine. It's all fine. Now that's double high five. Okay. So now we can put a whole bunch of masses there. Oh, look how they're coming back. So they don't really start there, but they do come back. Let's put this at 30 because I want to have a ton. And let's see if I can make this time for a little bit longer. Let's say 63 times 10 to the 6th. They're spreading out, but they don't go away. Like they're coming back. So you can think of it like a spring, and so they're oscillating back and forth, or like a hump, and they're rolling back and forth in this hump. Those other ones get ejected, so that's the problem with there. I think I could turn those off, but I like it the way it is. I'm pretty happy with this. I'm going to try and include as many links down below because I'm probably not going to come back to Lagrange problem for a while. So this is like my peak Lagrange point for a while. So I'll include the code down below. I'll include a whole bunch of the links, and hopefully you'll find this very useful. I have fun. I think it's artistic. Let me point out also that this is indeed in 3 dimensions. You can rotate it around, and I think that's pretty cool. Okay, so that's it for now. I'll talk to you guys later.